Okay, welcome back. We're going to talk a little bit today in this lecture about entity architecture basics. In other words, we're going to be talking about what the entity and architecture relationships are, the basic structure of an entity and architecture, and what are the elements of the entity and architecture. So we're going to start off by first off checking, talking about some standards for naming or naming conventions. When you write code of any kind, whether it's in a programming language like C or Python or a language like VHDL, it's good to have standard rules for how you name variables and how you name very special elements inside the design so that you have a consistency to your code and it makes it easier for others to view it when they understand those standards. I've worked in industry, and in industry we had books of standards for how we were to comment the code and variable naming and other things like that. So this is just a continuation of that idea where I'll standardize this nomenclature for these lectures and for this course, and then we'll use them throughout in all the examples, so there'll be a consistency to it all. First off, let's take a look at the naming conventions. And the first is the entity and architecture component. So anytime you name or you create an entity, you have to give it a name. Anytime you create an architecture declaration, you have to give it a name. And so we, as a convention, we will name those using a technique called upper camel case. Now, for those who may not be familiar with upper camel case, the reason it has the name upper camel case or camel case is because of the fact that the capital letters seem to make a hump if you draw a line around them. So let's take a look at what that looks like. Looking at the example that I've given here, you can see that upper camel case means the first letter is capitalized, and then the other letters are lowercase, and then the next word's letter is capitalized, then the rest of the word is lowercase, and then the first letter of the next word is capitalized and lowercase. So you get this hump structure. That's where the camel case name comes from. And then when we say upper camel case, we're talking about the first letter being capitalized. And doing this helps us identify and distinguish entity names from, say, a signal name. And so that's why we want to come up with these standards right now. Given that, we also want to look at naming of signals. And so when we're naming signals and variables, and we're going to talk more about what a signal and a variable is later, but when you're naming signals and variables, one of the things that you're going to be doing for that is starting with the lower camel case. So we want to use lower camel case for naming signals and variables, and upper camel case for entities and architectures. Now when it comes to constants, we want to use all caps like you see here. So all caps, and when we use an all cap for each word, we want to separate each word by an underscore. This is pretty much standard in all languages I've ever programmed in, C and Pascal and others. When you create a constant value, you use all caps separated by underscore. That's the only time you really see all caps because all caps is difficult to read for most people because of the block nature of the font. So if you're curious about this, you can go look up the difference between lowercase and uppercase and why lowercase is easier to read and stuff like that. But we won't get into that here, but it does work out better to limit the number of all caps things you have in your code. And because of that, I have a standard that I stick to, which is all reserved words are lowercase. And this means reserved words like entity, architecture, end, and, or, not, anything that's a standard word in the VHDL language will be all lowercase. Now, unfortunately, a lot of tools out there that auto-generate code will all make these capitalized, which is truly unfortunate because the emphasis shouldn't be on those. It should really be on the variables and reading the code more clearly. Another thing that you'll see is data types. You'll see people like standard logic using all caps, and that's just really not good practice in my opinion. So we're going to stick with for this course and for the code we do here, we're going to stick with an all lowercase on all the keywords in our VHDL code. I'm going to give some more specific guidelines to things to help us with naming. None of this is written in stone, but it is important, I think, to convey more clearly what your system's doing with the names that you choose. And so anytime we name an architecture, then we're going to be using the architecture name, and then we're going to tack on an underscore arc after that to really emphasize the fact that this is an architecture associated with an entity there. So that's a good naming strategy we'll be using. And then, of course, process labels, which we haven't talked about yet, but they are part of the VHDL language. The use of processes should also be all caps. So that'll be our naming standards for the rest of the series on our VHDL course here. Let's take a look then at the entity. So we're going to kind of dive right in and look at the entity and how the entity is structured and what the meaning of every element is. We saw in our first VHDL coding video an example of an entity, but let's dive a little deeper into the elements of the entity here so that we can get a better feel for what's going on. You'll notice that the structure starts off with the keyword entity, then the name of the entity followed by the keyword is, then we define the port. So basically in this part of the code, we're defining the ports for the entity. Now ports directly coincide with the actual block that we're defining. Remember, an entity is defining a block in hardware, and that block will have inputs and outputs associated with it. So the entity declaration, the port declaration in the entity declaration, will basically define the names of those inputs and outputs and the data types of those inputs and outputs. And a new term that we're introducing is the mode. Now the mode refers to whether or not it's an input or an output or an in-out, and we're going to talk about that in a second, but the mode has to do with really the direction and the way the port is configured as far as signal and how the signal is routed at the port level. So in this particular case, you'll see that we've declared 3 inputs, okay, switch 1, 2, and 3, and they appear over here as 3 inputs in our block diagram showing this component. We have the name of the component at the top up there, and then the input values inside the block to indicate this is a component. So this is how we would draw a component in a block diagram for when we're doing our designs. The next part of this is the outputs, okay, and that's our LED signals, and that corresponds to these outputs over here. And so the idea is you're defining each signal's output name, and you tell it it's an output by using the keyword out. Okay, and just like we told it it was an input by using the keyword in. Okay, sorry, that's my dog is barking in a car. So basically, this is the way we define our entity, and every entity will look very, very similar to this and have the definitions provided like this. Okay, so what we're going to do now is we're going to take a look at the port modes. Remember, we were talking about the fact that the entity has ports, and the ports have different modes, and we've seen the in and the out mode, and those are fairly obvious. An in mode is an input, and the out mode is an output. But we also have 2 other available modes that we don't see much, and we actually don't use an awful lot, but we want to talk about them so that you're aware of them. Now, a couple of things about the in mode. So if we let's focus on the in mode. The in mode, a port pin that is declared as an in, having a mode of in, cannot be driven by a source inside the component. So in other words, you can't have a declaration inside your component that assigns a value to an input. That would be trying to drive an input with another output, and we can't do that. Okay, so that's fairly obvious there. An input can't be driven by an internal signal because it's an input. All it is input information. An output, by its nature, cannot be used as an input. Okay, so a port declared as an output can't be used inside your design as an input. Now this specification can create some interesting and confusing problems that are fairly easy to overcome by just declaring an internal signal for that. But the idea is if you've declared an output, you can't use it as an input for another thing. So if you need a feedback path, like if you're creating a counter, you obviously want to take the output and wrap it back around into your logic so you can figure out what the next value is, right? So that feedback path, though, can't be done by taking the name of the output port and applying it inside your design. You would have to, in this case, create an intermediate signal in your design, which we'll talk about soon, and then use that as your feedback signal. Now, because of that very issue, the very issue that you can't take an output and use it as an input, we see that the buffer mode was created. Now the buffer mode's a little different in the sense that the buffer mode actually does allow you to take the signal and feed it back in. The problem with using buffer is buffer and out don't play well with one another. And designs that have buffer in them are difficult to interface to designs that use the out. And so what happens normally is the people that design these components tend to favor one or the other. It'll be all buffer or it'll be all out. And nowadays, I haven't really seen too many people using buffer. I think it's pretty much universally out and in as far as their choice of signal types. And so buffer is kind of faded into the background and just not used as much from what I've seen in the designs that I've done. So if we look at the last one here, we haven't talked much about, and that's the in-out mode. And the in-out mode is designed as a bidirectional signal. So the idea of an in-out mode port is something that you can either read information from or write information to. And think of that sort of like a bidirectional data bus. So if you have a memory chip, right, the data bus can be used to read values from the memory, or it can be also used to write new values into the memory. So the very same pins the data comes in and out of, not just going in and not just leaving, but it's a bidirectional system. So the in-out is used to signify that it is a bidirectional pin. And that's a little more complex to use. By and large, 95% of the time or more, you're going to be using in and out, and that's pretty much exclusive for entity declarations. Let's take a look at the architecture structure then, because the architecture structure basically has has two areas in it that are important for us to recognize and understand what their purpose is. We start off, of course, with the architecture declaration at the top. The important thing, we mentioned this before, is that the entity ties back to the architecture by use of the keyword of. So we're saying the intro arc, remember we talked about the naming convention of using arc at the end of the entity name. This is the name of the architecture, intro arc, and it is defined by or connected to the entity called intro. Now, intro simply defines the structure, the inputs and outputs in the box for our component. The architecture is where the meat of the component is. That's where the functionality is defined inside of our component. So now let's take a look at the other areas. So first off, inside the architecture, you delineate things by using a begin and an end statement. Okay, so you have a begin and then you have an intro arc here, and that separates this into two distinct areas. The first area is the declaration area. Okay, now the declaration area, right after you've declared architecture, contains things like your signals that you're using inside the design. It contains constant declarations. It also contains component declarations. So basically the declaration area is a place for declaring things that are going to be used inside of your design or your component. The definition area basically defines the functionality. This is where the function is defined. This is where how it works and how it's implemented goes. And so it also is important to recognize that this is called a concurrent area in VHDL, and a lot of people get confused with what concurrent means, the word concurrent means. And what a concurrent means is that each statement in the architecture's definition area is not sequential. In other words, the order doesn't matter. How they're positioned and how they're ordered inside the architecture really doesn't matter. All that really matters is that the statements are in there and each statement defines hardware. So this is a point where it's really important for us to recognize that we are defining hardware when we write VHDL code. We are defining how hardware is laid out. We are not defining an algorithm for execution at the time of the processing its information. In a microcontroller or a microprocessor, the code you write executes real time and is fetched and analyzed real time over and over again in order to achieve the goals, right? But in VHDL, we are defining a layout of hardware, physical interconnections of hardware, and then it's fixed. Once you've defined it, it doesn't change. That hardware is mapped in place. And so it's a very, very, very different process. So what I've got is a neat little example here that should help us understand this idea of a concurrent area and how concurrent code works. So let's start off with this example. And what I'm going to do is I've got two equations here. Okay, so we have two equations, these two equations here. The two equations are going to be used to define an output called y and an output called x. Now let's take a really close look at these equations, and we'll notice that y depends on both b and x, okay? Whereas x depends on a and b, okay? So because of that dependence of y on x, things get confusing for folks who are learning for the first time. So the idea is, if you look at this code from a programming standpoint, you're going, wait, I can't solve this problem. So you're telling me that a equals 0 and b equals 1. Remember, that's for a low and a high, a 1 and a 0. And then that if I tell you what those a and b are, I should be able to determine the values from that, right? So let's go through it, and let's start off here. We'll say, okay, y is equal to not b. Well, that's easy. So b is 1, so not b would be a 0. And x. Well, x is down here, right? So how can I use x before it's even defined? And that's what it means to be concurrent. It doesn't matter the orientation of these, it doesn't matter how they're laid out in the architecture definition area, because each of these lines is defining hardware, specific hardware, all right? And because it's defining hardware, there's no sequential nature to this. You don't start at the top and you work your way down. Since each statement defines a unique piece of hardware, all it is doing is just laying out hardware on the system. Okay, so that's it. It's just laying out hardware, and it has no beginning or end or start or sequence associated with it. What this does is it actually defines this hardware. So let's look at it and see, so we can have a better understanding of why concurrent, what it means to be concurrent, and why the order of these don't really matter. If we look at the statement for x, let's start with the statement for x. So we've got the statement for x here, and x is a or b. And so if our inputs are a or b, this represents the x, right? So what we've done is we have specified in our code that we want an OR gate, and we want the OR gate to have inputs a and b, and the output's going to be x. And that's exactly what that line does. Now, the order it appears inside my architecture doesn't matter. I'm defining hardware. The next statement, if we go to the next statement here, y is not b and a. So y is defined by this area of hardware, okay? So y basically takes b, inverts b, okay? So it takes b, inverts b here, and then feeds that into our AND gate, and that's where we do our AND X. So we AND that with X, and then we get Y. Now notice the order that these appeared inside the architecture don't matter, because each line is defining hardware, and the interconnections are automatically handled by the way you name your variables, right? So since we said X is equal to A or B, it's just the same thing as saying Y is the same as not B ANDed with A or B. And so the order doesn't matter. That's what it means to be in a concurrent system. So if you're used to thinking in terms of programming language in a sequence of things, that can really throw people. I've seen a lot of people who are learning VHDL for the first time get really, really confused by looking at code saying, wait, that can't happen. I haven't defined it yet. It's up here. Well, it's not about defining variables in a sequential process. It's about defining hardware with each statement. Okay, and so each statement defines hardware. So hopefully that clarifies things a bit. As we get more into it, it'll become clearer, I think, later on. The last concept that we want to talk about as far as the basics of entity and architecture is every entity can have an architecture associated with it, okay? So every entity can have an architecture associated with it, but every architecture can only have one entity with it, right? So you can every architecture is defined by one entity, but you can define multiple architectures for the same entity. Now, why in the world would you want to do this? What's the advantage of this? And the advantage is actually quite nice. So let's say that you're trying to create a complicated design in VHDL. You've got multiple parts and you've got multiple people on the team. And let's say that design, well, let's make it simple. We'll say it's 2 parts. And we've got one person working on the stuff that's going to be a communication protocol. We'll just call it some new communication block. And then we have somebody else working on a display block that handles displaying information onto some sort of device, LCD screen or whatnot. And they want to work together and create a part of this big project, right? And so if we have these 2 pieces, the people can go away and start by defining a simulation architecture. Now, the difference between simulation and a regular synthesizable architecture is that a simulation architecture doesn't necessarily have to run on hardware. And you can use some really fancy statements inside VHDL that allow you to simplify your code and make things a lot easier to implement in software. Right? So think of it as a software test, right? So you're going to be creating a simulation model for the system that will simulate the behavior your component will do once you define it in hardware. So when you create this simulation model, you can hand it to the rest of the team and say, here's our model and here's all the interfaces. And then you can run a big simulation of the whole system to make sure everything works the way you expect it to in a simulation run before you start investing time and effort into creating actual hardware. This is a very valuable step. It's also a fairly quick step. Like I said, writing simulation hardware or simulation architecture, is a lot easier than writing a synthesizable block of code or a block of hardware. And so once you've done this, then you can run away and start making your actual synthesizable architecture that you can map to physical hardware. And that's a valuable thing, because once you've built up your hardware block, you can test it against the other people's simulation architectures in simulation. So you can simulate your synthesis architecture against other simulation architectures to make sure it all functions right. And once you've done that, then you can move to hardware. Okay, it sounds more complicated than it really is. Basically, you're writing a little test architecture to say, okay, this is how it's supposed to work. And then everybody puts it together, and yes, if we can do this, it'll work right. And then you go away, you actually write the synthesizable architecture, which can be mapped to actual physical hardware, and then you start putting it in your FPGA or your CPLD. Now, the other 2 blocks I'm showing here as far as architecture are I often discourage because you normally don't want to design your architecture to target a specific type of device. And we talked about how CPLDs and FPGAs are the dominant programmable logic devices on the market, and the architecture inside a CPLD and the architecture inside an FPGA are incredibly different. Because of that, you can write VHDL code to optimize for one or the other of those architectures. So for instance, if you're using an FPGA, the FPGAs have enormous storage resources, flip-flops galore. And because of that, you can implement state machines using a thing called one-hot encoding, and we'll talk about that in later videos. But it focuses on an architecture that is heavily register-based. Now, if that's the case, then if you try to put that architecture inside a CPLD, which is just the opposite, it's more combinational logic based or strong in combinational logic, then your design is going to be awful, right? So you really don't want to generally design for a specific type of architecture, but you can. So if you are working and you've created this wonderful component, and you're trying to get it into a particular device like a CPLD because the cost is low and you're really pushing the limits, you might want to tweak your architecture for a CPLD by changing a few things to make it optimized for that environment, and then it will fit better. The problem with that is it becomes less portable. You can't port it to the FPGA very easily if you've designed it with that CPLD in mind. So typically we discourage that. You basically would almost, 95% of the time you would want to target a generic architecture or declaration of your design so that it can be used in any of these devices easily. So typically that's where you want to head. You don't want to really focus on the middle, but you can, okay? If your design really requires that kind of optimization, it's possible to do that. So the bottom line is one entity declaration can have many architecture declarations for various different reasons. Typically it's for simulation, but you can do it for other reasons too. I've done this for when I'm trying to test out two solutions, right? I was designing a custom communication protocol one time, and during the process of doing the design, I was wondering, well, is it going to be better to use a register-based process, or is it better to use a large state machine process? And so I tweaked that and kind of played with it to see which one was more optimal for performance. So you can, and I had two architectures declared that I could kind of play with. So that kind of comes up sometimes as well. But that's it for our discussion today. That's our entity and architecture kind of in a nutshell. Next time we'll start getting more specific into modeling styles and such. So we'll see you next time. Thank you.